Welcome back. This time we're going to look at applying these ideas of flux and potential to not just one charge, but to two charges, in the particular case of a dipole. Firstly, what is a dipole? This here, one positive charge and one negative charge quite close together, they form what is known as a dipole. They are equal charges. It's just that one of them is a positive charge and one of them is a negative charge. There are going to be flux lines, therefore, that emerge from the positive charge and flux lines which go into the negative charge, because negative charges attract unit charges and positive charges repel unit charges. Now, what happens when these charges are brought together? What do the flux lines look like when they're kind of in between these two charges? We can start to work that out by considering the forces on a particular unit charge some distance away from the dipole. Let's consider the force on this unit charge here. It is being attracted to the negative charge in the dipole. That's this blue arrow here, the attraction force. It's being repelled from the positive charge in the dipole. So this is the repulsion force here. Now they're not quite parallel, which means that there is a small resultant force in this direction here. Now, the flux lines have a direction which is the direction of the force on a unit charge. So the flux lines at this point here would be pointing in this direction, and they'd have quite a small density because these forces almost cancel each other out. The net force on this unit charge here is much smaller than either the attraction or the repulsion force. So we know the flux lines at this point here are going in this direction. What about the flux lines at that point there, directly in between the two charges? Well, any unit charge there would be being repelled in this direction from the positive charge and attracted in this direction by the negative charge, so it would be experiencing quite a large force in this direction. So we would have a high density of flux lines directly in between the two charges in the dipole, pointing from the positive charge to the negative charge. Flux lines emerge from the positive charge and end up at negative charges or infinity. So we could draw them like this, and there's quite a lot of them because the forces on a charge there are quite big. The repulsion force and the attraction force directly add up together. So there's a high density of flux lines between these two charges in the dipole. As you move further away from the dipole, the density of the flux lines gets much smaller. At this point here, a unit charge would be attracted by the negative in this direction and repelled by the positive charge in this direction. But the force of attraction to the negative charge would be greater than the force of repulsion from the positive charge, because the negative charge is closer. So the lines of flux at this point here would be pointing straight towards the negative charge. If I carried on and plotted where the directions of the flux lines were all the way around the dipole like this, I would end up with a diagram like this. There are other ways to derive the mathematics behind these patterns, but that'll have to wait until second year. Now, what about potential? What about the total amount of work that it's required to take a unit charge from infinity to somewhere around about a dipole? And this is energy that is acquired by the electric field. It's worth pausing at this point to consider why I'm writing this as V. Does this have anything to do with voltages in circuits? And the answer is yes, absolutely it does. Consider this potential here. This is the amount of energy that's required to move a unit charge from infinity to a particular point in the circuit here, a distance r away from a charge Q1. Now, supposing I wanted to know the energy I needed to move this charge, this unit charge, from here to here. I could work out the total amount of energy that I needed to get from infinity to this point here, and that would be the potential at this point here. And I could work out the total amount of energy I needed to get from infinity to this point here, and that would be the potential at this point here. I could call this V1 and this V2. The difference between V1 and V2 is the amount of energy that I need to take a unit charge from this point to this point. Just that distance. I could say the potential difference between these 2 points is V1 minus V2. And that potential difference is the energy required to move a unit charge between these 2 points. However, remember the definition of a volt. 1 volt is the potential difference such that 1 joule of energy is required to move 1 coulomb of charge, a unit charge. Voltage is defined in terms of the energy required to move a charge between those 2 points. But that's exactly what we're calculating here when we're calculating the electric potential. So this potential difference here is a difference in voltage between these 2 points. Same thing. Now, consider this one. How much work is required to move a charge Q from infinity to halfway between the charges in a dipole? Well, the wonderful thing about potential is that it's proportional to the charge. Which means it's linear. Which means that I can do this. The sum of the potentials is the potentials due to the sum of all of the charges. And the total potential is the total amount of energy that it would take me to move a unit charge from infinity to a point, a distance Ri away from all of the charges Qi. Here I've got 2 charges, a positive charge and a negative charge. So I'm a distance d over 2 away from each of these charges. So the amount of work I need to do to get my charge Q, a distance d over 2 away from this positive charge, is Q times Q over 4 pi epsilon naught d over 2. The amount of work I need to do to get my charge, a distance d over 2 away from this negative charge, is minus Q over 4 pi epsilon naught d over 2. Negative because my charge is being attracted to this negative charge. So I can extract energy from allowing this charge to move towards this negative charge. It's where it wants to go. The total amount of energy that I need to spend is therefore 0. It takes no net energy at all to move a unit charge from infinity to that point there directly between the 2 charges in a dipole. Okay, that's all I wanted to say about dipoles. Next time, we'll be introducing Gauss's law, which is a very powerful technique for analysing problems in electric fields.